Okay, so 15.6 is on surface integrals, and so this is just, an analog, a 3D or 2D, however you want to view it, analog of a line integral. And so remember, sort of the idea, if you have some curve like this, the line integral over that c of some function, the integral over c of the function, right now that function is a function of x and y because you're moving through space here. That integral, you don't put dy or dx here, you put ds, right? Because you're thinking when you break that up, you want to take little slices of the arc length so that you move along there correctly, right? And so I don't want to try to draw the picture here, but look up at the computer's or the book's picture here. If you have your book with you, you can look at that. But there's the analog to it, right? So the idea was that for an ordinary integral, you were down here, right, and you were splitting this up into little pieces. For the line integral, you needed arc length instead. And so we do the exact same thing over here. For an ordinary double integral, you're integrating over this area, right? And so those are your little dAs. You want to do the same thing as you integrate over a surface, but rather than talk about dA, you want to talk about ds, or change in your surface area, so that if your surface is really, flowy, bends a lot, that you're incorporating that whole thing over that little patch that you're going to work over. Okay? And so I guess I'll just do very little work. So now you have a function of 3 variables, right? And you're moving over some surface, and so this should be your formula. And let's come up with what that formula looks like. Maybe I don't want to do all that much to it. Remember, suppose you have some r that's giving your parameterization now of a surface. That's what we talked about in the last section. Then the ds is just the magnitude of the cross product of the r sub u and the r sub v, right? That was just our surface area formula last time, and then dA. And so that's going to get put in here every time. So let's just try. I'll write down the formula and then we'll try some examples. So just like with double integrals and all kinds of other things, you have a definition on one hand, and then you have how we evaluate these in practice on the other hand. Okay, so the integral over a surface S is this. Okay, and then in practice, we evaluate it by integrating over the d. The d is your bounds for your parameters, right? And then f, and the point is you plug your u and v in to your function, and or your r of u, v, I guess. And then I'll just write it, the magnitude of r sub u cross r sub v, dA. And so this is our formula that we'll apply, and we'll say, so here, S is given by r of u, v over d, right? So the d's are the bounds for the u and the v. The S is just the surface that you're sort of going over. And I guess I'll note in the one particular instance, note if your S is just given like this, so this is still a parameterization, right? If z is given as a function of x and y, that should give a surface over some d. If you have that set up, your parameterization is just x, y, g of x, y, gives you a nice parameterization. And then if you take so it's x, y, whatever, you'll get 1, 0, g sub x, 0, 1, g sub y for your derivatives. And when you take your cross product, this formula just pops out, and so I'll just write it over. So in that case, I'll just write it like this. So if this is the case, here's our formula we'll use instead. Okay, so we'll just plug in the G for the Z's wherever those show up. And then your ds, again, this also just goes back to your old formula for surface area. It's G sub x squared plus G sub y squared plus 1. Hopefully that looks familiar, right? That's the old surface area formula for a function of two variables. All right, so let's try an example. And I think to demonstrate, we'll try this in two directions here. So, let's see. Okay, so evaluate this surface integral of the function 6xy ds over the surface S, where S is the part of, just write it like this, x plus y plus z equals 1 in the first octant. All right. So, and like I said, I think I'll do this, or at least set it up in two different directions. Okay, so first part, what does this surface look like? So it's the piece of this plane, right? That's in the first octant. This is a what plane? What's that plane? 1, 1, 1, right, for all the intercepts? Is that what you're, I'm assuming that's what you're tracing through the air meant, right? And then, so the top of this, you could view like this. S is 1 minus x minus y, right? And then your D is this region down here, right? The base of that thing. And so let me pull the D out. So in terms of just x and y, your D is just this triangle here, right? That's your D. Does that make sense? So you're going to convert, so we're just going to use that second form there, the f of x, y, g of x, y, and so on. So let's try that. So our surface integral well, let me just write it out. 6xy ds becomes, so it becomes the integral over the d of, well, f of xy of g of xy. In this case, your g of xy doesn't need to show up because no z shows up, right? So this will just stay g sub, or 6xy, and then the ds will be replaced with, well, I'm going to just write it out. Yeah, it'll be square root of 3, but it'll be z sub x squared, right? Z sub y squared 1. And again, where the z in this case is the parameterization that you have. And so the z sub x and the z sub y are both what? In this case.
Larger than 0.
0, 0.
Well, so no, what's z sub x?
0, 1.
1.
Oh,
I just want them, they're both -1, right?
Yeah.
Yeah.
You take your partial derivatives. I guess I wasn't asking the right question. So that gives you d sub xy. I knew you had it right because that's the right thing. So it's -1 squared plus -1 squared plus 1. Oh, this should have been a dA here, right? dA. Okay. And so now we look at our d, and I'll just go this order, dy dx. So what are the bounds on my
0 to 1 minus x.
0 to 1 minus x?
0 to 1.
0 to 1, right? Just the same bounds you would have always done. And so the only thing different is you have this square root of 3, but this shouldn't be too bad. So let's just work this out. 0 to 1, I'll just put the square root of 3 here. What's the integral of 6xy with respect to y?
3 y squared.
3x y squared, right? And 0 to 1 minus x. that okay? And then what? 3 root 3 x times 1 minus x squared dx, right? And then you can multiply out that mess there. 0 to 1, 3 root 3. And then it's just going to be x times what you get when you square that, right? Which will be 1 minus
Oh,
2x plus x squared, and then you'll multiply out by x. So it'll be x minus 2x squared plus x cubed, I think. Does that sound okay? All right, and then that'll give us 3 root 3 x squared over 2 minus 2/3 x cubed plus x to the 4th over 4, 0 and 1, so 3 root 3, 1/2 minus 2/3 plus 1/4. So let's, what does this give us? So 3/4 minus 2/3, right? Speak up if I screw up there. 3/4 minus 2/3. And so that's 3 root 3,
Over
9 minus, 1 over 12, right? Yeah, so it'll be 1 over 12. So root 3 over 4.
4.
Is that okay? Okay, so let's look at the exact same problem, but let's just tweak our formulas and see how it works. So it'll be almost the exact same work. But this curve, so we'll keep this problem the same, or this surface, I should say. We could have also viewed it as 1 minus x minus z instead, right? Y equals that. And then what's your d if you're viewing the surface as a function of y now? What's your d become? You don't need to give me the formula, but it's where is the d? So now I'm viewing y as my first variable, right? And if I get rid of y, I'll collapse back into the
Z equal
xz plane. So this would be my d down here now. This triangle in the zx plane. Does that make sense? And so your d this time would be in the zx plane. Again, same exact formula, right? Z equals 1 minus x. So now try to redo the problem, but just from a different point of view, right? So now you're, rather than z equals g of xy, you have y equals g of xz, right? And everything should work exactly the same. You should be able to sort of move to a convenient variable when necessary. So take 2 minutes here to try to set that up. Okay. So, again, if you turned your head, the only real difference, right? You don't need to even define this r. I'm just, here could be your r, or you could have done your s's, right? Y equals g of xz, as I said before. Maybe that's the better way to look at it. So y equals 1 minus x minus c. So when you convert over to the other form, you first have to, you're moving to just x and z, right? So your d is now over x and z, and so you have to get rid of this y and replace it by what it equals. That make sense? And then what's the ds? I mean, it turns out to be the square root of 3 again, but this time you should think of it as what? Oh, sorry. Y sub x squared plus y sub z squared plus 1, right? And again, you'll get a square root of 3, and your bounds, ds. Oh, that's fine. Let's do ds over d. And so again, you'll end up with a 6 square root of 3, and then x. I just leave it like this, 1 minus x minus z. And if we do dz dx, it's the same setup as before, right? And if you go ahead and integrate that, you should get the same thing. It'll be a little messier because you have more stuff floating around. But the point is, know to go to look in the convenient direction. There's no reason why, you know, I gave this specific formula when z equals g of x, y. That's, you know, if it's better to see y as a function of x and z, or x as a function of y and z, and your life is easier, then do that. So for the example we just did, I would say, you know, the z as a function of y was slightly easier. And so in another example, this might be the slightly easier way to go about it. And so pick whichever one seems better. Okay, let's try a couple more here. Okay, so this time I just want to do the integral over s of z ds, where s is the upper half of a sphere of radius 2, and I'll just say centered at the origin. Okay, if I put this on a test, there's no guarantee, but there's a very good chance I give you a parameterization for this surface. I'd say that follows this parameterization, but let's try to come up with that first. And I think the example we did to start class today, the homework from 15.5, the first one, should be a good should give you a good idea. Remember, we had a surface of radius 5, or a sphere of radius 5 there, and we modeled part of it. So now we want to do the same thing for a sphere of radius 2, and we want to go all the way down to the plane. We just want the top half of it. Does that make sense? So see if you can come up with a parameterization of this, and my hint will be, right, the natural way should be as a function of theta and phi again. So, like I said, there's a good chance on a test I might give you the parameterization, but let's practice that. As long as we're here. See if you can come up with that in a few minutes. Okay, so I'll let you do the rest of the problem. Let's just make sure we're on Same page. So what did you get for parameterization here?
Cosine theta, sine phi.
Okay.
Two cosine theta.
Okay, 2
Cosine theta,
cosine theta
sine phi.
sine phi 2
Sine theta.
sine theta sine phi
Two cosine phi.
cosine phi. That makes sense? All right, same thing we did before. And then this time, we want the top half, so what are the bounds? Theta goes from
From 0 to pi over 2.
0 to 2 pi, and then the phi goes from the 0 to pi over 2, right? If you wanted just the portion in the first octant, what would you do? What would be the change? So, a part of the sphere in the first octant.
From 0 to pi phi.
Um,
And the theta from 0 to
Not 0, so 0 to pi over 2 for both of them, right? Because you just want to do 90 degrees in both directions. Does that make sense? So the first one, the one we have, right, you're going all the way around, right? And so your theta goes all the way from 0 to 2 pi, and then this way, if you want just the first octant, then your theta is only ranging from there to there, and your phi is still going down like that, right? Okay. So try to finish this off now that you have this parameterization. Again, you're just going to plug these in for x, y, and z. You want to compute r sub theta, r sub phi, take their cross product. Go from there. All right. So let's just work through this together. So we first need the r sub theta, r sub phi, and so what do we get for these guys?
minus 2 sine theta
Minus 2 sine theta
sine
sine phi,
phi. 2
2
cosine theta.
sine theta sine phi. Oh, and then 0. Here. And then with respect to
2 cosine theta cosine phi.
2 cosine theta cosine phi,
What? 2 cosine theta.
2, I lost track of where we are. Oh, sine is still theta, right? Sine theta cosine phi, right? And then minus 2 sine of phi. Is that okay? All right. And so, again, it's a little bit messy now. You got to take the cross product of that thing, right? Which isn't the prettiest. Prettiest thing in the world, but let's just do that.
Zero plus 4 cosine theta sine phi square.
Alright. So, you'll get this minus 0, right? And so it'll be
Either way.
negative 4 cosine theta sine squared of phi. Is that okay? And then your middle term will be, right, it'll be negative, and then it'll be this times this, and then minus 0, so it'll be negative 4, and then what, sine theta sine phi, sine squared phi. Is that okay? And then your last term should be what?
0.
0?
I think so.
Minus 4 plus 4. So 0.
Let's see.
I think so.
Minus 4 no.
So how are you getting 0? So you get sine, it's this, right?
Mm-hmm.
So it's sine squared.
Yep, and
Sine
sine
cosine.
C, and
Oh.
sine C is the same. Was-
I guess I'm not. So let's just write it out. So you're gonna get negative
4
4
sine C.
sine squared of theta
Oh.
sine of phi cosine of phi, right?
Mhm.
And then what do you get the other way? Minus again,
Ah.
minus 4 more, and it should be cosine squared of theta, right?
Yep.
And then you have sine of phi.
I got it wrong.
Is that okay?
Yep.
I don't like when you're wrong, it makes me second guess. All right, so, let's see if this goes up.
Try from the back.
I know, that's what I was just gonna do. Last time that worked for no apparent reason. Did it again. Perfect. Okay, so before I go ahead and compute values here, what's this guy clean up to?
Back to 4 sine phi cosine phi.
Yeah, so notice there's a sine squared and a cosine squared, right? So if you pull everything else out, that's the same. You'll have sine squared plus cosine squared. So I'm just gonna write that like this. Is that okay? And so then we're not interested in this thing itself, but what? The magnitude of it, right? So we want the magnitude of this mess. And so we get square root of, well, a whole bunch of stuff squared. So let's pay attention to what we got. So we got 16 cosine squared of theta sine to the 4th of phi plus 16 sine squared of theta sine to the 4th phi plus 16 sine squared phi cosine squared of phi. Does that look okay? Alright, so now clean stuff up. So this is a little bit ugly, but
16
so
cosine C.
yeah, I mean you can clean up, let's just clean it up one piece at a time. So cosine squared plus sine squared of theta, right? And then otherwise those are the same, and so you'll end up with 16 sine to the 4th of phi, right? For just the first two. And then you have plus 16 sine squared of phi, cosine squared of phi. But now again, you have cosine squared and then there's a sine squared in there as well, right? So you can pull out, I'll just do it one piece at a time, 16 sine squared of phi, and just in case you don't see it, that leaves you with sine squared of phi plus cosine squared of phi, right? Which is just 1. Does that make sense? And so this whole thing should reduce down to just sine 4 sine of phi. I suppose technically it's 4 absolute value, but again, we're only allowing, the phi only ever ranges from 0 to pi. and sine is always positive there, so you can always drop the absolute values. Okay, that's a whole lot of work just to do that little bit. Come up with this. So now, I'm back over here. So the integral we are interested in is this one. And so let me just rewrite it. So the integral over s and t by ds becomes what? The integral now over the d, I'll come back to the d is just the bounds, right? The simple set of bounds there. So this will be easy to integrate once we get it set up. What goes in for our z?
4 sine phi.
Well, actually, let me write it this way. F of x, y, z, right, and then magnitude of, well, I'll write it this way. F of x, y, z, all right. R of theta, theta, d. I think I'm going to leave it that way. I finally figured out how to write it. I guess I did theta first. It doesn't matter which one is which. Write it in the same order. Right, so now we know what this is, and then F was just z, and so we plug in the z component. So what is it?
2 cosine phi.
Okay, so the z here just becomes 2 cosine of phi, and then we decided it was 4 sine of phi, and again d theta, d phi, 0 to 2 pi, 0 to pi over 2. So 0 to pi over 2. 0 to 2 pi. Do this however you want. 2 sine cosine is sine of 2 whatever, and so this can become 4 sine of 2 phi, phi theta, phi, or you could do a substitution of u equals sine or cosine, right? Either way will be fine. Integrate that with respect to theta is just going to give you what?
8 pi.
Yeah, so it'll be this times theta, and so when you plug in the 2 pi, you'll get 8 pi sine of 2 phi. And then integrating with respect to phi should give you, I'll just write 8 pi times what?
Cosine negative
Okay, good.
over
And then
2.
over 2, is that okay? And then again, 0, pi over 2. So when you plug it in, you get cosine of pi, right, which is
0
negative.
negative.
-1, and so it'll be 8 pi over 2 minus a negative, so it'll be plus another 8 pi over 2 when you plug in the 0. So I think you should just get 8 pi. Okay? All right. Any questions so far on that one? All right, let's try another one that's very similar. So I won't put the directions up here. Compute this surface integral, the integral over s of y ds, where s is just, well, let's do this. Okay, so x squared plus y squared equals 3. What kind of surface is that?
Cylinder.
A cylinder, and then you want to range between
0 inches.
0 and 6. So when you set this up, right, the x and y are only going to depend on one parameter, and then the z will depend on the other. So you should kind of have 2 distinct parameters. So see if you can set that up. again, if you haven't gotten this far yet, I'll just write up the parameterization. So you could use whatever variables you want. I'll use u and v just to stick with our other form. So what did you get here? Here, I'll start it like this.
Square of 3 cosine u.
Okay, good.
And square of 3 sine.
3 sine of u. So that part, right, if you ignore the v, that'll give you a circle of radius 3, and that's what you want. And then you want to go up and down. And so your bounds for the u are 0 to 2 pi, and your bounds for the v are 0 to 6. Jen? Yeah. And then the rest of this one, hopefully, is pretty straightforward. So if you feel like you know what you're doing, just keep plugging away, and I'll slowly write up the stuff you need. Is that what you guys got? Okay. All right. So then what's that magnitude? Root 3 cosine squared plus root 3 sine squared plus 0. So it's square root of root 3. So yeah. Just write that out. Square root of 3. Okay. So now just plug everything in this case. Well, let's just do it. So the double integral over s of y ds. So what's the y get replaced with?
Square of 3 sine
Sine of u, and then the ds.
du dv.
Well, okay. du dv, and in this case they're just fixed, right? So 0 to 2 pi, 0 to 6. Okay.
I got 0.
What's up? You got 0?
Yeah.
Okay, that seems reasonable. Let's just double check. I guess we'll get it right away, right? So 0 to 6, this will give you 3, and then the integral of sine will be negative cosine of u, right? And then 0 to 2 pi, and cosine at 2 and 2 pi and 0 is the same thing. So you should end up with 0 here. Does that make sense on our, based off of our function and our region? So what's our region again? It's a cylinder of radius square root of 3, right? You get this. And then we're integrating just y, right? And so whatever positive y's you have on the right-hand side, you get the negative y on the left-hand side. And so it makes sense that it all sort of canceled out correctly. Okay? So again, I don't know that I would try to notice that. I would just do the work, get 0. But whenever you get 0, think about it for a second. Does that seem to make sense? And I would say in this case it does. Okay, let's try a slightly uglier one now. And I think rather than, let me just write this out and then we'll see if you agree. So I want integral of s of y plus z ds, where S is the surface with, so this is going to have multiple pieces to it now. Sides, x squared plus y squared equals 3. Top, c equals 4 minus y. And bottom, x squared plus y squared S are equal to 3 in the xy plane.
Equal to 3?
Yeah.
Equal or less?
No, less than or equal to. So it's the whole, that's a whole disk then, right? So your whole insect. So let's draw this region before we do anything else, and then hopefully I can convince you what's going on. So we just saw what's x squared plus y squared equals 3. It's a cylinder, right? And so this, I'm going to just draw it like this. You're going to get a cylinder of radius 3, right, coming up. And then at the bottom of it is just the circle of radius 3 in the xy plane. So you just think of that cylinder sitting on the ground, right, or on the xy plane. And then that cylinder gives way to this, I say circle, I mean the whole disk, right? So it's the whole flat bottom. And then the top is some plane. Again, I don't care exactly what it looks like, but it just wedges through this region. And so you're going to get something that looks more or less like that. Does that make sense? So you have a cylinder coming up, and then you slice it with a plane at some angle. That's what we have. So I'm going to say S1 is this part. What order? It doesn't really matter what order you do it in. S2 is this part, and S3 will be the bottom. Okay? And so the book spends a little bit of time giving you the formula, but hopefully it's pretty easy to realize what happens, right? It's the same thing that happened when you had intervals and you pieced them together, or if you had different regions and you pieced them together. The integral, the double integral of S over S, these are again surface integrals, should be the same thing as if you just do it over each piece and add them together. Does that make sense? And so that's how we'll go about this. So we'll do each piece separately. So this first part, that should look very familiar to what we just did a second ago, right? Because you're going around that surface. I guess you got to be a little bit more careful. Well, I'm going to let you play around with it for a second. Yeah. Try this first. So maybe before I even do the integral, let's just do this. S1. Try to describe that region and then integrate over that region, and then continue on for the other two pieces. Okay. So for S1, we want to go over that surface, right? And so you're still, your X's and Y's are all just spinning around in a circle. And so you're going to get the same thing we did before, root 3 cosine theta, root 3 sine of theta, right? And then let's just say Z here. And you could use a different variable. I just went with theta and Z this time for whatever reason. And so same setup as last time. The thetas spin all the way around, but your Z's only go up to where?
4 minus 1.
Yeah, so the Z, it's 0, Z, so 1 minus, or so 4 minus. Y, in this case, what is Y?
Square root of 2 sine.
So Y is yeah, it's this, right? Root 3. So I'll just squeeze it in right. 4 minus root 3 Does that make sense? So those will be your bounds on this one. So maybe we'll just go ahead and do this integral as long as we're here. So over S1, y plus z ds. And so, again, the y and the z just go in for themselves, so it's the integral of root 3 sine of theta plus z, and then
For here, can I just put 4 in,
for what?
for x plus z? Because if you move these to the other side, x.
Oh, you could do that, you could do that.
Oh. This is easier.
I don't know, that'd be fine, I guess. D, let's see, dv, d theta, right? And your bounds are just what? 0 to 4 minus square root of 3 sine of theta, and then 0 to 2 pi. Is that okay? Okay. And so then just go ahead and integrate that thing. It should be pretty straightforward, I think. Right? And in fact, I think I'll just put down the answer. You can double check my work here, but if I did it right, I didn't write down my work. I just wrote down the answer. I got this. So double check that, but it should be, you know, pretty straightforward from here. How about S2 then? So now you're just going over that surface on the top. So how would you parameterize that guy? So this one, I'll just say, is already given to you, right? Z equals 4 minus y. And so you can just use that form that we were using before. Oh wait, you know what? I take that back. You can't let z equal y minus, or 4 minus y, because you're on the outside of the surface, right? So you can do it. You could do it in this case when you're up here, but not when you're going around the side.
Got you.
Okay. So anyways, there's our parameterization. Right. This time you're looking at z as a function of x and y. Let's come back to that in a second, and I'll just set this up. So this thing becomes, right, the surface integral over S2 of y plus z ds. So now you are on this surface. Now you can replace that with 4 minus y, right? You get this. And then I guess you could do, wow, let's zy, or zx is 0, zy is -1, right? And so your bit that goes here is the square root of 0 squared plus -1 squared plus 1 squared, right? Okay. And then dA, I don't want to call this S2 anymore. Now this is over the D, right, which is really it's really the same as S3, the region down in the xy plane. And so you end up with the double integral over D of what, 4 times the square root of 2, I guess, dA. And then this time, what is your D? It's it's the circle of radius square root of 3 down in the plane, right? And so you could, I suppose you could convert to polar coordinates and do it that way. Or you could just realize that if you integrate a constant over a region, it's just, I'll just write it out, area of D, right? And so what's the area of that D? Well, it's a circle of radius square root of 3, so it's pi times 3, right? Square root of 3 squared. And so we should just end up with 12 root 2 pi, I guess. Yep. All right. And then finally, the last one I think will be the easiest one, or easier one of them. So where are you at? You're down in the plane, right? And so what is z equal to?
0.
Yeah, z is just 0. again, you can think of that as your g of x, y, right? And so your z sub x and your z sub y are both 0, and so your ds is just the square root of 1 dA, right? 0 squared, 0 squared. So you're just going to do this. So it'll be your integral over S3 y plus z ds just becomes the double integral over d of y dA. Oh, yeah, that's fine. Does that make sense? And then how do you integrate y over a disk of radius 1? You should convert to, or actually maybe we could just,
Polar coordinate.
you could convert to polar coordinates, or maybe this time let's think about it ahead of time. So I would say in practice, probably your best move is to convert to polar coordinates. But we're integrating y, we're integrating the function y over this circle, right? Of radius, doesn't really matter what it is. So what should be the answer?
Sorry, pi.
No. You integrate y over this. Whatever happens for a positive y, you have a negative y down here to cancel it out. It's going to be 0. So you can double check your work, but you should get 0. If you want, you make that, what, r sine theta, r d theta, right? And the integral is from 0 to 2 pi, and so the sine, integral of sine will be 0. Is that okay? All right, so that's a big mess, and so your final answer, right, the integral over the full surface then of y plus z ds is just the sum of these things, right? So 29, assuming I did that right, plus 12, 2 pi, and I'll just say plus 0, because. But if you have a bunch of different pieces, and it's sort of natural to describe them in different ways, then you just break up your integral into the surface integral over those pieces. Okay, any questions so far? All right. Okay, so let me be lazy. Let's do this. Okay, so suppose you have some R, and it's a smooth, orientable surface. Again, I don't want to draw. Here, I'm going to let the book do some of our work for us. So we talked a little bit, I don't know if it was last time or the time before, about what a smooth, orientable surface, about what it meant to be orientable. And I gave an example of the Mobius strip, remember, where I took the piece of paper and I folded it over, and there was no clear top and bottom, because if you walked around one side, you sort of ended up on the back side. And so everything that we're going to state here for surface integrals for this next part is only going to hold for orientable surfaces. So you have to avoid weird things like that. But most surfaces are orientable. And so, work my way down. I just didn't want to draw 50 pictures. Okay, so here is a surface. Okay. Oh. So here you have some surface, and so the ends are going to point out. And so how do we compute the ends? Well, if you think back to when we did tangent planes of stuff, right, the r sub u and the r sub v were supposed to be pointing parallel to your tangent plane, and so the normal vector was the cross product of those two guys. And so that's what we have here. Now, depending on how you decided which variable was which, you'll get an arrow either, so if you got a surface like this, your arrows will either point up or they'll point down. But the point is, if it's orientable, they're all going to do the same thing. They're all going to either point up from your surface or down from your surface, and then if your surface bends, you'll stay sort of on the outside or you'll be on the inside. And so if you just have a generic surface like this, we don't care which one you call the normal vector, but they'll be, it'll be convenient to point one direction or the other. But the point is that the normal vector can be either r sub u cross r sub v or the other one. And then we're going to scale them to make them unit normal vectors. So we divide by the magnitude of that thing here. If we have a closed surface, like a sphere, we always want to pick the normal vector to be the one pointing out of the sphere. But otherwise, we don't really care if you're pointing up or down. It's only when we're closed we want to always say, we'll agree that the one pointing out is the normal. Does that make sense? Okay. And so let's see. And so I'll just say this. We take the normal vector, 2b, and again, it's what I just said, RU cross RV over the magnitude of that guy, or negative that same thing, right? And then I'll just say, I'll just say it in words. If S is closed, we take it to point out. And again, if we're in the situation where our surface is just given as z equals g of xy, we have a simplified formula to this, which is just simply negative gxi minus g sub yj plus 1k over that's that same magnitude we saw back in the last section, right, when we talked about surface area. I guess it's section. But anyways, come up with that equivalent formula. Okay. What do I want to say? Right. So, I guess this is a definition. The surface integral of a vector field now. So we have f is, I'm just going to write it like this. Okay, so now we're talking about some surface sitting in space, and maybe the picture from the book will be easier again to use than to describe it. So here's sort of the picture from the book, right? They say, suppose you have this field, the F, running through a surface, right? And so you could think of it as the F representing, I don't know, the velocity of some fluid, right? You got some fluid flowing through some surface. That's kind of the standard way to think about this. And so the formulas, well, they give you this right here. So you really want to be measuring the volume of fluid that's passing through. And so they give you a measurement here. The volume is essentially the height of this, which comes down to just calculating what they have here. And so the takeaway is that the line integral, so we call this a surface integral, right? Just like we had with line integrals, we had line integrals over vector fields. This is the equivalent. You want to have surface integrals over three-dimensional vector fields. And you just have, well, you have what you can see here, right? S, the surface integral over this guy is just defined to be this, f dot n ds. Okay, so that's the definition of the surface integral of f dot ds is f dotted with n ds, but then, right, we know what n is. just write it out, I guess. So N is R sub U cross R sub V, right, over the magnitude of R sub U cross R sub V, but so is ds. ds is the magnitude of RU cross RV dA, and so those magnitudes cross out like this. And so in practice, you compute this integral by crossing those guys out and doing F dotted with the cross product of those over the region D that's defined by the U and the V again, okay? And so I would imagine, yeah, that's what they're saying on the next line, so. Okay, so let's just try an example, see how this goes. So, fine, I guess fine. Formula F dot RU cross RV dA, and here the F, right, is evaluated by plugging in the R into it. And so again, formal definition is this, in practice, this is how we evaluate it. And then we'll see, remember when we had line integrals, we saw that the ones that came from the dot product of a vector field with that, we had the fundamental theorem of line integrals we could call on, and we had Green's theorem that we could call on, right? And so we'll have versions of things similar to those that we'll use to actually evaluate these in the future, but we'll just sort of go at this blindly for now. Okay, so let's do an example. And so this is also, just like in the other case, this line integral is called the flux. So the flux of F across the surface S. So find the flux of F you see that's a 0. There's 0 y z, 0 y negative z across y equals x squared plus z squared if y ranges from 0 to 1. So, see what you can do with the setup here. I'll give you 2 seconds to work it out. So again, come up with a parameterization for that surface. I didn't say. I'm going to call this S across. Surface S. Let's define that. All right, so what's this surface look like? Not a cone exactly, but a paraboloid, right? It's opening up as a paraboloid in the y direction, so you get right, and then you go off from 0 to 1. So you could come up with all kinds of different parameterizations. You could do stuff where you're getting circles and other kinds of interesting things here. But where I would say the easiest parameterization is just this, right? xz, x, z, and the y is x squared plus z squared. Now there's some drawbacks to that, but let's not worry about those too much yet. So when we look at that parameterization, where do the x's and the z's range? So we're going to let go xz, the y is x squared plus z squared. That's exactly our surface, right? But what x and z's do we want to consider?
From 0 to 1.
Well, from 0 to 1 and 0 to 1 would give you what?
0 to this one.
Here, let's pull this up again. So this was a drawback I had said we had with, I don't remember where it was. So here's a parametric surface. Let me, all right, so you could have used this parameterization, right? This would give you the right thing now, where y is equal to x squared plus z squared. So this parameterization would work. That's fine. And I warned you last time that you should be careful, because if you pick the one where you just sort of do it blindly, so let's just call it x, right? X squared plus z squared, and then z. And then I think what you said was you'd have them both go from 0 to 1, right? And you'll see you get the wrong piece, right? You get, oh, I think you said negative 1 to 1, right? Same problem though, is from negative 1 to 1, right? You still aren't getting the whole surface, right? You're losing these little pieces there because you're integrating over a whole rectangle. But what should you really be integrating over? Not a rectangle, but a circle that corresponds to that, right? Does that make sense? And so this is over, I'll just write it this way, x squared plus z squared less than or equal to 1, right? Over the unit disk. Does that make sense? Okay, so now let's just follow, I guess, this form right here. So the flux is the double integral of s of f dot ds. And again, in practice, we get it to be, well, I guess let's evaluate all this stuff before we do that. So r sub x, sorry, I'm all over the place here. R sub x is just what, 1, 2x, 0, r sub z, 0, 2z, 1, right? And so what's their cross product?
Two x,
That?
2x1, 2x, then 1,
2x,
then 1.
negative 1 actually, right?
Then 2x.
Then 2,
2z.
let's see.
2z.
Yeah, then 2z. Okay, so 2x, negative 1, 2z.
One,
Yeah.
one.
Isn't it negative?
Yeah.
The middle term is
Yes.
always negative.
Yes.
Okay. So you get this, and so now we're going to do this, right, crossed with f of that, and so let me just write it this way. It'll be over our region f of your vector, right? In this case, we made it a vector of x and z dotted with your cross product. Yay. And so let me just write these as vectors. So it's, again, 0 still, what's y? Get replaced with your parameterization. So x squared plus z squared. And then z, negative z is just z, just negative z still, right? That make sense? And then dotted with that cross product that we just computed, so 2x, negative 1, 2z. Does that make sense? And so what do we end up with here? 0, x squared plus z squared,
That's it.
negative, minus
2z squared.
2z squared d
Z.
a. So I guess we end up with
That's it. That squared minus 2z squared.
yay, okay. That's fine. And then you're going across the whole unit disk, right, in the x and z plane. And so how would you evaluate that integral? So, just write it this way. Z and x are here, right, and you're going across the whole disk, 0 to 1. And so don't get bogged down that it's x and z now. You can switch to polar coordinates, right? You're in two variables, and you're going around a circle. So switch to polar coordinates. Just treat x like you would normally, and z as though it was y, right? And so what do you get? Negative, what was it? I pulled the negative out. So x is r, well, r squared cosine square root of theta minus, or sorry, plus, I already pulled out the minus, 3 r squared sine squared theta, and then r dr d theta, right? And then just go ahead and integrate that. I don't know, you can clean it up a little bit, I suppose, but, oh, and then what are the bounds here? 0 to 1 and 0 to. All right, I think well, let's just work it out. So, negative 0 to 2 pi, 0 to 1, r cubed, right? And then cosine squared plus 3 sine squared dr d theta. So negative 0 to 2 pi. With respect to r, we get what? R to the
4 is over 4.
r to the 4th over 4. So we'll just end up with 1/4, right? And then
Cosine 2 theta.
where are you getting that from?
1 plus 2 sine theta squared.
Oh, okay. So, yeah, let's do, so you could do, I think you're fine. I think you're a step ahead of where most people will be though. So let's just work it out slowly. You could do, this isn't the way you are suggesting to do it. I'm going to do it a slightly different way. Or maybe it was 1 plus, so you went to cosine now.
Yeah.
I'm going to write it this way, 2 sine squared theta,
Cos
d theta.
and we have over 4.
Oh, yeah. Pull that out front. So negative 1/4 out front, and then you have that. And now you could,
You only can put it into cosine, I think, because it's squared.
well, so you could do this in all kinds of different ways on the surface, right? But you eventually have to integrate the sine squared, and so this is 1 plus, and so the way to integrate it is to shift it to be this. 2's cancel, and then you end up with negative 1/4, 0 to 2 pi of what, 2 minus cosine of 2 theta. Is that okay? And so we end up with negative 1/4, 2 theta. It doesn't really matter what we have there, but it was minus sine of 2 theta over 2, right? The whole sine stuff is just gone, and so we end up with 4 pi there, so there's negative pi for the final. Does that make sense? All right. So some of these take a while. Let's stop there. I think I'll start with one more next time, just to get us comfortable with, just to remind us of what's going on here, and then we'll talk about the divergence theorem, which is sort of an analog of Green's theorem. It'll be an easier way to compute these guys. So, all right.